Good day. Today I'd like to ask a question. Is your white paint a murderer? Who's the victim? Color pigments and the paint itself. And what is a murder weapon? Photocatalysis. So let's look at this in more depth. So why are white paint murderous? White paint contains titania oxide and zinc oxide, and they can have photocatalytic activity. Now, photocatalytic activity means it accelerates the degradation of paint when it's exposed to UV light. So that's when your paint is in the sun. So paintings by various artists has already been found to contain harmful photocatalytic pigments. So this is for real. So let's first explain how does photocatalysis work. So over here, in the middle, you see these titania. That is your white paint. So that's the pigment of your white paint. Here you have UV light. So that is like sunlight. And then it goes through a process. So this happens in the titania, and it causes the oxygen and the water to form radicals. And those radicals are very reactive, and they then react with anything that's organic, whether it's pollutants, paint or pigments. When you look at the research, most research of photocatalysis are focused on pollution. So there's a lot of information about that, not so much on paint itself, but there are a few articles. Most research are focusing on degrading pollution. So photocatalysis is very, very valuable to clean water, but the same photocatalysis can cause problems for artists. So it can degrade your paint to such extent that it turns into carbon dioxide and water. So this is an example of yellow dye. You can see up here, there's a dye molecule. Those in the red are what photocatalysis are forming. Those are the reactive radicals. So now your dye and those reactive radicals react with each other, and your dye then breaks into pieces. So this dye molecule, this big molecule that's complete, it breaks into pieces, and when it's breaking into pieces, it loses color. If photocatalysis is happening, your pigments will not be light fast any longer. When you put them in the sun, photocatalysis will cause radicals, and the radicals will cause your pigment molecule to break into pieces. So here's an example. Here we have Pyrrole red and Hansa yellow, and when it was put into the sun, you can see that the color is changing with time. Yes, it took very long. So under normal conditions in your house, your paint would not degrade like this, but if you put it in the sun where there's a lot of UV light, then you see this degradation. I must say there are various mechanisms of degradation in UV light. Photocatalysis are not the only one. So now you can see when it was not diluted the paint with white, you don't see a change in the color, but when it was diluted with white, you can see a change in color. So now the question is, do we see this change in color due to a concentration effect, or is the white paint causing photocatalysis? So let's first just look at the concentration effect. Let me explain what that is. So imagine you have a bag full of sweets and you eat 2 sweets. You're not really going to notice it. But imagine you only have 3 sweets and you eat 2 sweets. You're really going to notice it. So when we go back to this slide, yeah, there's a lot of pigment molecules. So if a few of them degrade, you're not going to really notice it. But when it's mixed with white, then you have less of those red pigment molecules available here. And that's why a change is more noticeable. So if you are having a mixture of white and red, and a few of your reds get degraded, you're going to notice it much, much faster than in the case when there's many of those pigments. So not all white paint are equal. They might have the same chemical formula, but you do get different types of titania, and it depends on their crystal structure. So according to this article, they are talking about some titania being photocatalytic active and some being photostable. Now, in my mind, I don't agree with this word photostable. I will give you some proof in a future slide. I'd rather say it's just less active. So all titania is catalytic active. It's just a question of how much. So the specific type of titania that's stable is called rutile. So here are pictures of rutile and anatase, and you can see both are white. So with the naked eye, you're not going to see a difference between those two types of titania. And the difference is in how those crystals are packed. There's another third type of titania called brookite. So over here, when you look at this picture, here in the middle, that blue sphere, that's your titanium, and then you have your oxygen around it. So that Ti is titanium, and that's oxygen. So the blue spheres are the titanium, and the red is the oxygen. So you can just see how it's packed. From a chemistry point of view, they consist of the same components, but the way they are packed, their crystal structure is different, and different crystal structures leads to different photocatalytic activities. So here's a phase diagram. So this basically shows you get brookite when you're at low temperature and high pressure, and you get anatase when you're at a low temperature and low pressure. So if you just make it at room temperature, your titania, you will form anatase. That's actually the most stable form of titania at normal conditions. But when you heat that anatase, it will convert to rutile. This is basically the same type of phase diagrams, maybe just a bit simpler. You can once again see if you take your anatase and you heat it up, you form rutile. Now remember, rutile is the one that's a better type of paint, a better type of titania paint, because it's less active as a photocatalyst. So a manufacturer can change the type of titania in their paint. All they do, they take the titania and they heat it up above 600 degrees Celsius, and the anatase will turn into rutile. So basically what happens, these crystal structures change. So this anatase, which is stable at low temperature and low pressure, will rearrange and form rutile. And rutile is the one that's got a lower photocatalytic activity, and rutile is the one that we want in our paint. So the manufacturers can also test it. They can use XRD or Raman to check what phase they have. And you can see those peaks are different for anatase and rutile. So it's very easy to check. Most universities have XRD equipment, and some universities have Raman. And it's very easy, those equipment. I mean, I have done that type of analysis. It's fast, it's cheap. If you have the equipment, there's no reason for not doing it. If you don't have your own equipment, you can outsource those analyses to universities. So the manufacturers have no excuse not to test and make sure that they have the correct phase in their paint. So they can check and make sure that they have rutile, which is the safer pigment in their paint. So this is just to show you how rutile and anatase differ in terms of its photocatalytic activity. So here at time 0, this blue was put on different types of titania. So on the top and the bottom, this blue ink was placed on anatase. That's now the bad titania pigment. And over here, it has been placed on rutile. And here, it's been placed on something that does not have photocatalytic activity. So this is just like a baseline. When they've now placed this 4 strips in UV light, that's now UV is like sunlight, but it's now UV from a lamp, and you can see after 50 minutes the color has already changed, and after 90 minutes it has changed. So in the case of the rutile, there is no color change. In the case of the baseline, which does this component do not have any photocatalytic activity, there is no color change. So from this test you can see that the rutile titania is the better form of titania, because after 90 minutes we did not see any color change, and anatase is an unwanted titania pigment, but this is only after 90 minutes. So here a test has been done after 2 hours, so you can see the different crystals, SEM analysis, and when you look at the different type of organics, you can now see the different photocatalytic activity your different types of titania have. So remember now, rutile is the one that we want in our paint. And when we look over here, so the longer this bar is, the worse the type of titania is for paint. So the bigger this bar, the more active it is for photocatalysis. So we want short bars. So this rutile, you can see when it was, the organic was ibuprofen, it's short, and when it's phenol, it's short. So over here, it's very similar to anatase and rutile. You can see a bigger difference between the anatase and the rutile is because ibuprofen is more difficult to degrade than cinnamic acid. So you can see the difference between the different type of catalysts much clearer when you have a more difficult organic to degrade. So you can see now when it comes to the most difficult organic to degrade, which is phenol, and it's difficult to degrade because it's got aromatic features. You can see that the rutile has a very, very low photocatalytic activity. So this just shows you that rutile is definitely the phase of titania that we prefer. So we want rutile in our paint. We do not want anatase or brucite in our paint. But the other thing I want you to take note of, this is not zero. So even though rutile is the better titania, it still contains some photocatalytic activity. Over here, you can see it was only 90 minutes. Here, it was 2 hours. And we want our paint to last for decades. So even though the rutile has only a very low catalytic activity, it still has activity. So over here, I think they simply didn't wait long enough. So if you wait long enough, all the type of titanias will have photocatalytic activity. It's just the quantity. So yes, if you have anatase in your paint, your color will degrade faster than when you have rutile. But in both cases, there will be degradation. So even though we have rutile in the paint, I mean, this is coming from Golden, this example, and Golden is the most reputable and respected acrylic manufacturer, so I'm sure they will have the correct phase, but even if they've got the correct phase, you still see degradation. So what to take out of this slide is rutile has got the lowest photocatalytic activity. But even though it's got the lowest photocatalytic activity relative to the other forms of titania, it still has some activity. So white paint will cause some photo degradation. So now why is the different types of titania different? So now going into a bit of heavy chemistry, so you have UV light, it shines on your titania, your rutile or anatase. You see here's a valence band, so it excites electrons from the valence band to the conduction band. So this H plus just talks about holes, and then your electrons are excited. Now that excited electrons then reacts with your oxygen to form this type of radical, and your hole is then reacting with your water to form this radical. So, and these radicals then cause the degradation. Now this position of these valence band and conduction bands, those positions relative to each other differ for the different types of titania. So we talk about the band gap and also the absolute positions of these two bands. So over here we can now see that band gap and the position of those two bands are shown here, and you can see for the rutile, anatase and brucite they are different. So this is a background why anatase is more active. Furthermore, if you look at this slide, if you look at the crystals over here, normally a smaller crystal will lead to a higher surface area, causing also faster activity. So there's two reasons in this case why the rutile was less active. You can see this is very big crystal, so the surface area would be less, so the rutile for that reason will also be less active. So there's two parameters modifying the activity of the particular titania pigment. So what can we do? Well, golden has got some varnish called archival varnish, and you can see it has quite a marvelous effect. So if you have your control now without any varnish of this archival varnish with UV protection in it, you can see it degrades, and after just 2 sprays it's much better, and after 6 sprays of this UV protected varnish you can see almost no degradation. So I would recommend that we varnish our paintings with varnish that has a UV protection in them, because it really makes a difference. What else can we do? We can test our own white paint. We can make mixtures of organic pigments with the whites and do a light fastness test by placing it in the sun. So here you can see I find that a blue hull rating of 6 and higher is good, or a ASTM rating of 1 and 2 is good. So if your paint can last this long in full-blown sun, then we can say under normal conditions it will last for decades. But if your mixture change color say in 2 weeks, then you know that white paint is really bad. So I would really recommend that you start taking your white paint, mix it with dyes that's organic. You can look at the structure, you can just Google it. If your structure looks something like this, then it's an organic paint. So organic paint, you see there's some carbons and some hydrogens, then you know it will degrade. But if you are using inorganic pigments like iron oxide, they will not degrade. So all organic paints will be susceptible to photo degradation. So yes, unfortunately white paint can be a killer. So yes, all white paint are killers. It's just a question of how fast can they kill. So we want rutile in our paint because that's the paint that kills the slowest. So yes, please make sure that you are using white paint. That's a slow killer.